Okay, ladies and gentlemen, it's 1 o'clock, so we'll get started. Very warm welcome to the EBRAINS session at this year's EOSC symposium, which is just getting underway as we speak, and we are delighted to have the opportunity to present EBRAINS at the outset of this year's conference. So what is EBRAINS? I will say a few words about that. My name is Paweł Świeboda. I'm the CEO of EBRAINS, and I'm delighted to be joined here in the room by Professor Jan Bialy, professor of the University of Oslo, and the Infrastructure Development Director of the Human Brain Project, and the head of EBRAINS Scientific Services. Online, we will be joined by Professor Petra Ritter, who is head of the brain simulation section at the Charité Hospital and also the head of EBRAINS Health Data Services. So the three of us will speak first. And if you have any questions as we speak, please don't hesitate. We are in this rather intimate setting, so we can definitely relate to what you are most curious about. And then we will have some questions and answer time at the very end. So what I will do is I will introduce EBRAINS, tell you a little bit about what we do and how we are organized. And then Jan Bialy will speak about how we approach the open science paradigm in brain research. And Petra Ritter will speak about the EBRAINS solutions, so how we are ensuring user centricity. So if we can get started, let me say first of all that neuroscience is experiencing a very special period right now. This is a clipping from The Economist's Technology Quarterly from September of this year. I would strongly recommend that you reach out for this if you haven't read it. It's a very interesting set of articles, but the argument is that neuroscience is undergoing a renaissance, as The Economist puts it. And there are several reasons for that. What the paper argues is that it has to do with scientific advances, but also with the new technological means which the research community has at its disposal. One could add to that it is also an increasingly significant policy priority, and therefore there is more attention given to this field. The rationale is that of linking the healthy, the interconnected and diseased brain. We're watching a growing awareness of the significance of good brain health among citizens at large and in policy. And surely the burden of brain disorders is also becoming increasingly evident to policymakers, given the aging of societies and the prevalence of brain disorders in an aged society. As a result, we have a unique policy momentum at this point in time with respect to how brain health is treated and how it needs to be supported by brain research. And here you can see just a few examples of the most recent policy developments globally, in fact, because this is clearly a global priority with a strong anchoring also in European policy. So in May of this year, we saw the World Health Organization adopt unanimously its action plan on epilepsy and other neurological disorders. The European Commission followed a month later with its Healthier Together initiative on non-communicable diseases, with a separate chapter on mental health and neurological disorders. Several European countries, Norway among them, are also working on their own brain plans, so their own agendas for approaching issues of brain health. There is a lot of community-based efforts, and the One Neurology initiative especially led by organizations such as EFNA, are worth mentioning in this context. And last but not least, there is renewed attention given to mental health, both in the US and in Europe. In the United States, there is the US Mental Health Strategy, pursued as of a few months ago, and the President of the European Commission launched at her State of the Union address in September the new European Mental Health Initiative. So that means a lot of policy momentum takes place as we speak globally and in Europe. Now, EBRAINS is there to support brain research, which is then to lead to better brain health solutions. And we do that by decoding the multiscale brain, because one important characteristic of the brain is its multiscale organization. So brain data has a particular degree of richness and complexity. That's also why we exist as a domain-specific research infrastructure. This type of a challenge cannot be successfully met by other more horizontal research infrastructures because of the uniqueness of brain health, of brain data, and the way the brain is organized and what it takes to capture brain dynamics. Just to give you some numbers to illustrate this, 86 billion neurons with 10,000 connections, that takes us directly into a comparable framework to that of studying the universe. 100 billion stars in the galaxy, compares well with 86 billion neurons, even though each neuron has these numerous connections, which multiplies the scale of the challenge, especially for computing purposes. And if you look at the third bullet point here, it's also a bit of a comparison between astronomy and brain research, namely 2.3 million kilometers of fibers in the brain and diameter of the sun with 1.4 million kilometers. So there is something to the complexity of the brain that puts our fields in the same category as those of the most complex brain, the most complex scientific challenges. No? I was trying to now play a video, but let's see if this works. Okay. It started to play for a moment, but then it's, or maybe no. Yes, it is playing, so that's a very short journey into the human hippocampus based on the 3D polarized light imaging performed at one of the EBRAINS facilities. And I think what it helps to demonstrate is the degree of detail that is now that one is now in position to study. Given the growing resolution of the different brain atlasing techniques in this case. And this resolution is constantly improved in order to see ever greater degree of detail. The brain atlases are now moving in the direction of 1 micrometer, enabling us to study cortical layers, fibers, and the type of processes in the brain which were not within reach of scientists only a short moment ago. And all this takes an enormous amount of computational power, including for storage purposes, and especially when it comes to the different simulation experiments. And you can see some of the data of what even a second of simulation of large brain networks, what it means in terms of computing needs at the supercomputing facilities which we use. Now, a word about how EBRAINS is organized and where it comes from. So it is emerging from the European Union flagship Human Brain Project, which is a 10-year scientific and infrastructural endeavor, and now in its final year, ending in September 2023. The Human Brain Project has had two sides to it, one being a scientific program to study the human multiscale connectome, and the other one closely related, the development of a research infrastructure to study the brain further, called EBRAINS. We are active in three disciplines. Brain research, neuroscience is our main discipline to start with. We're increasingly active in brain medicine. But the third, and also very important nowadays, is brain-inspired technologies. EBRAINS offers a range of services right now, starting from the data and knowledge services that Jan Bialy will speak more about, moving on to the brain atlases, a glimpse of which I have just shown you. The brain atlases are there for reference, because imaging cannot be provided to study the entire brain of every individual and to take account of the human variability. So therefore, the brain atlases have been created and offered to the community as reference tools. Then we have the simulation and the modeling and simulation services, which enable us to generate virtual data and complete the picture for research purposes, and brain-inspired technologies such as the neurorobotic facilities enabling us to perform virtual experiments, and last but not least, services which have to do with health data. Our philosophy is that of data amplification, namely working on standards and having in mind that the use of standards then generates reuse of data, but also accompanying user journey and helping researchers to deal with the scientific problems, developing solutions through high-end analytics, and hence encouraging researchers to share the data. So the very philosophy is that of incentivizing data sharing. And one particular focus of our attention is what we tend to call the EBRAINS knowledge loop. And that's the whole cycle that starts with data generation, that takes us through the modeling and simulation phase, that completes the existing data with virtual data, and then we go into various model validation and inference tools in order to be able to extract value from data. So again, EBRAINS is not just a data platform. We very much rely on being able to extract value from data. And that approach takes us to the field of integrating different types of data and enabling solutions such as the digital brain. I will maybe, in the interest of time, say a few words about the need to be responsive to science, because surely tools and services are good in themselves, but they are only as good as the scientific advances that they enable. So to paraphrase Louis Besson, a neuroscientist who has published a fascinating book called Entangled Brain in the recent months, well, he speaks about the risk of being able to measure every cell in the brain, but doing so in a theoretical vacuum. So we definitely have to avoid that risk, and we have to do this by enabling scientific progress and theoretical progress also, in order to make sure that data sharing serves a purpose. And that what it takes is also for us to have to pursue a certain degree of methodological and conceptual rigor, namely for the different hypotheses to be clearly presented, for the assumptions and premises on which they are based to be clearly explained at the beginning of a research project, Secondly, for sufficiently large samples to be studied, that's also one of our objectives at EBRAINS, to make sure that brain researchers have the cohort data that enables them to draw sufficiently viable conclusions, including through the use of AI algorithms. Thirdly, we need to correct for multiple tests, adjust the number of variables, and then what is also enormously useful is to be able to publish both positive and negative results. So this methodological and conceptual rigor is what needs to come on top of the different data tools. Ourselves at EBRAINS, we are increasingly active in the field of health data. And we have joined enthusiastically the pilot project to prepare the ground for European health data space as a breakthrough solution in the field of accessibility of health data. So we are one of the 3 research infrastructures involved in this pilot project. And we accompany the legislative work which is currently going on to make access to health data possible in the context of 2025 on a much stronger footing. We also contribute to what we call the New European Brain Initiative by being part of an effort to develop Brain Health Partnership. This is planned in the Horizon Europe context from 2025 onwards, but also to develop a Brain Knowledge Hub and make sure that the neurotechnology platforms achieve sufficient effect of scale. And finally, what I would like to say today is also that we are here today for a reason, namely that we are a proud and committed member of the EOSC ecosystem. So building on our commitment to open science that Jan Bialy will speak about in a moment, we are preparing our tools and services to be interoperable and discoverable via EOSC. We are in technical discussions about this. EBRAINS AISBL, so the association which is mandated to run and operate the EBRAINS Research Infrastructure, is applied to join the EOSC association. And finally, we plan to become an EOSC service provider with a catalog of services, hoping to achieve policy alignment. So we are strong believers in the value added of EOSC. Some of our tools and services have been developed as part of the EOSC approach, and Petra Ritter will speak about those also in a second. So we are very open to contributing also to the development of EOSC so that it works in the interest of the research community and so that it also enables easy access to tools for researchers at large. So I will end here and now invite Jan Bialy to speak about our philosophy of open science and how we approach the fair data paradigm. We just need to switch the slides here. Maybe. Okay. So let's sit down. Would you like to?
You have it on the...
It's on the desktop.
Is it this one? Right.
No, it's on the desktop. That's it. Yes, thank you very much. Oh, is this the right one? Here we go. That's good. So I will walk you through or go a deep dive into one of the services we have in the EBRAINS Research Infrastructure, EBRAINS Data and Knowledge Services. But I'll do that by actually first looking a little bit into the challenge, the content. What is it that we are dealing with? So the brain is not possible to study unless you go through many levels, many spatial scales. At the top of this figure, you have the subcellular level, the details of structure and function inside neurons and other cell types in the brain. As you go down, you go into cells, you go into the networks between the cells, you go into brain regions and the whole brain. At each of these spatial scales, from the smallest to the biggest, we have many, many data acquisition types, many instruments, many data types. In addition, we have the temporal scale. We have data that are collected based on molecular changes at picosecond scale up to changes in the aging brain, for example, over years. So, this heterogeneity, multiple scales, spatial and temporal, that's what we have to deal with. So the researchers coming in with data, we refer to them as data providers usually, they come in at one or more levels, and then they jump over to the other side as data consumers, or general researchers, of course. So most people are in both roles. Others come in from the consumer side, and they may, over time, find more and more data at each level that allow them to do better research and combine their own data with available data. At one single level, you have many different complexities. So, for example, for a brain region, here illustrated with human brain, you have different subregions according to a number of criteria. You have different features inside these subregions, and you have connections. All of this represented with different data types. So we often use atlases, just as they do in geography. Today, when you work with data from the Earth, maps of the Earth are really critical, of course. And this is the same with the brain. And maps can contain information of different types and different levels of granularity and different scales. So atlases work as integration tools. Here, illustration with animal model atlases on the left side, one of several types, and on the right side, human brain atlases, which are able to integrate different types of information. All goes into the same spatial coordinate system. And then around this, we have, as Pavel Triboda explained, also the modeling and the simulation environments at different scales again. So to the left, the whole brain level, in the middle, the single neuron level, and to the right, more details on how these neurons function and what's happening within their arborizations, for example, their detailed local circuits. So basically what I'm going to talk about is how do we bring all of these different data types together through a curation support mechanism, bring them into a data service where the metadata will exist inside a knowledge graph, where the data are accessible, and where you can connect this to different type of computing services for analysis. So here they are, the different services we have in the EBRAINS Research Infrastructure. Data knowledge is what we'll be talking about now, but they do exist, the data knowledge services, in the context of these other ones as well. They're very much connected. So for example, the access to HPC computing goes through community. The tools available for many types of analysis are in the other blobs here. But what is our real motivation for this, if we look at it in some broader terms? Well, it's part of the digital transformation in neuroscience, obviously. It's obviously related to the replicability and reproducibility need. We are all aware of the fact that much of science today has problems in this area. It's of course a contribution to open science, initiatives to remove barriers for sharing of any kind of outputs, resources, methods, tools. And it's because simply data are drivers of science. being aware of having access to high-quality data analytical tools is clearly a driver for science. And also because we consider ourselves to be part of the 21st century digital data stewardship implementation. In the 17th century, the journals came along. It was difficult, was a hard struggle, wasn't popular. People were afraid of sharing through journal articles. In the last century, we exposed data sharing. It wasn't popular, it was difficult. No, these concerns are no longer particularly interesting to discuss. It's there, just like the journals were there a few hundred years ago. And we are there to deliver fair, trust, and care. Those are the three principles that have really been very helpful with the references shown on the slide. Fair, of course, that speaks to data, metadata. It's equally important for everyone involved. Those who contribute data, those who use data, those who build services, everyone has to think through the FAIR principles. Helping data to be possible to find, access at some level, to be possible to interpret and reuse. Then we have the trust principle, which is mostly speaking to the way I see it, mostly speaking to the data repositories or the services. So this is about making sure that everything there in the services is transparent, it's focused on users, it's sustainable, and so on. This is speaking to us as service providers. And then we have the society around this, and everything around data governance, perhaps, which is related to authority to control, responsibility, ethics questions, and other societal perspectives on the collective benefit of what we're doing. So these are very important motivations. So then what is this particular service? It's a service facilitating sharing and access to research data, models, and tools. It is delivering consistent data, quality assured data, and we'll walk through a little bit how we deal with that. And it's also focused on the governance, defining terms of use, responsible compliance, and data protection provisions when required. So how do we do this? Essentially through three different elements. One is a knowledge graph. Second is a metadata model or metadata framework. And the third is curation of what's coming into this. So now a little guesswork. What is this? Well, it looks like a three-dimensional structure. You can see it's moving. And if I tell you we can add something to it quite easily, then it becomes obviously four-dimensional. It changes over time. What we're looking at here is the EBRAINS knowledge graph. That is a metadata management system, organized network of real-world entities with nodes and links and labels. It connects all the metadata. And it is very smart because it allows us to add something as we go forwards, which is absolutely critical. We need this flexibility in this field. And we cannot just populate it with anything. Well, we could, but then it would be very difficult to compare information coming in. So we need some standards for the metadata. And in this regard, we have worked, for example, with the International Neuroinformatics Coordinating Facility and with other projects around the world to establish a standard. This is referred to as Open Minds. And it's, of course, obviously then shared. And it's built into our knowledge graph. And it is used by our curation services. So the curation is critical because it really organizes the metadata. What does it do with the data per se? Our curators do not go in and tell people with all their complicated instruments that we don't like your data. The data producers, the data providers are responsible for the data, but they can receive advice on how they should be structured and presented. And of course, quality tests at a more technical level. But the metadata this is where we have to give something to the data providers to allow them to map onto something which is comparable to what others are doing in the field. So we can have a domain-specific metadata enrichment that gives tremendous value. So the steps involved are shown in the diagram at the bottom here, starting with ethics regulatory compliance check, which is usually not very difficult because people have organized this thing, but if there would be an exception, we would discover it. Structuring the data in an understandable manner, then providing some tools to add the metadata, writing a data descriptor, choosing a license to tell others how they can use the data if they found them, and then provide services for uploading data to long-term storage. We can also allow only pointers to storages elsewhere, so that we only keep track of all the metadata and expose those. But if we do that, then of course that other service needs to be persistent. So then around this there's essentially two services. One for sharing, coming in with data, then you go through the curation. And as you go here on the curve to the right, you increase the level of fairness. You add information. The more information you add, the more fair you become. So journals are requiring this, funders are requiring this. You need to come up to a certain level. But if you can, and it's a little bit like pieces in the puzzle are kind of coming together. So you start to see how things are related to each other. That's the basic curation. But if you continue and work more on this, then the picture becomes more and more clear. That's the advantage of a more advanced curation, and the value goes up. But to go into the system, a basic curation is a requirement. The other service is find data. That is exposed both directly online through graphical user interface, where you simply write in text, you search, or you use faceted search filters and create your own search in a simple GUI. Or you do it programmatically. You use our query builder and API. It's not particularly advanced, so you don't need to be very programmatic in your mindset, but it allows you then to have full access to everything in the knowledge graph. All of these services, the share service with the curation and the find service on the graphical user interface is available to the entire community. We do have a filtering obviously on the data coming in, but we can take quite a lot of data from the community. If you want the query builder and API, you need an EBRAINS account, which you can get easily if you are at the research institution, university, or other relevant location. This is all connected, of course. So from left, data, model, software coming in, going into the knowledge graph, all the metadata explaining what this is living inside the knowledge graph with the curation in between. And then when you've found something in the knowledge graph, you look at it together with tools, with workflows that's available in the system, and you can then do science in a new way. So how do we communicate about the EBRAINS data knowledge services to the data providers? A quite common situation is that you have researchers that would like to make their data available with a journal publication. So can we help with that? Yes, we can, because we have a track for publishing research data alongside a journal article. We develop it together with Nature Scientific Data. They were tremendously helpful. But it's a generic track, so it's not for a particular journal. So this works well for anyone who wants to go along with their paper and then prepare for sharing at the same time as they publish, or they might prefer to share or even before. And we can also then allow reviewers to have access while the paper is in review, and in the cases where the provider would like to wait until publication with release of data. Another situation is that researchers are saying that the data from my research is of a foundational nature, I want to easily find back to them myself, look up anywhere on the planet, all the data I have. This is the way to do it. And also make sure that the data can be used in future research. We have quite a few collections coming in now of this type of data, where researchers are seeing that this is really essential to get out. Of course, the experience they have is either they are so, what should I say, experienced and far going in their research career that they don't bother if there are any peculiar things inside the data, or they are the most bold young researchers who realize that yes, when I share my data, there can be a few things that looks a bit silly, and that's completely natural. Those are the winners of the future. So they can go into this service and thereby allow this type of foundational data to be available to the community. We have several external projects that have come in. These are 3 examples. They have nothing to do with the funding for our service. They come from elsewhere, but they have used the service to share their collections of data of various types. Some examples shown here in what we call data cards that you can find in the graphical user interface. And then from there you go onto the data. You will find the metadata, you see how you get the data, how you can cite them, and so on. Now, we all know that access to data is a critical point. Levels of access and conditions for access. So, when it comes to animal research data, under most circumstances they can be easily shared, as long as the regulatory compliance has been met, the experimental phase. When it comes to human data, it is different, of course. Human data can either be, as we see on the lower row, non-identifiable. They can be very strongly pseudonymized. De-identified is what the Americans would say, meaning that all direct identifiers are taken out and most of what you can think of indirect identifiers are taken out, but in principle there could be something left which would allow identification of an individual, like saying that, well, we have a part of the brain here, we're seeing it, and maybe it's some unique aspect to it, so it could be kind of a fingerprint. And then you have more generally pseudonymized data or raw data where you see more. So different levels of control is needed. So for the non-identifiable human data, you can have open access, or they can be under embargo waiting for release. But when it comes to either strongly pseudonymized or pseudonymized, you need control of some sort. Restricted access is a term here used to refer to a set of restrictions before you get the data. For example, we have a system for this which we call the Human Data Gateway, which can be helpful for a few cases of data sharing. You need an EBRAINS account, you will be tracked, and you have to sign up to a number of conditions around the access. But in most cases, you need a fully controlled access, where you are inside a secure environment. And you will hear more about this also from Petra Ritter, and this is a huge area of importance in Europe now, to get these services for controlled access up and running, being efficient, creating an environment to work with data in that category. So if you want to hear some more about the background and details of data publishing and this EBRAINS Data Knowledge Services, we have a Nature webcast. It's quite easy to find by searching for example, making small data big and EBRAINS, and you will see it. So you can just go in there if you want to hear more about that. Also perspectives from different external users. And this type of work is possible through collaborations among many teams dealing with different parts. So we, for example, have to the right the Knowledge Graph team, which is based at EBRAINS. At DMU UK, we have data governance teams. and the other teams are working on different aspects of general data, experimental data, human data, model, and so on, models and so on. So that's my walkthrough of EBRAINS Data Knowledge Services. Thank you very much.
Thank you very much, Jan. We will have time for a discussion after the third presentation, and we will now switch to the online connection. And I give the floor to Professor Petra Ritter from Charité in Berlin and head of EBRAINS Health Data Services. Petra.
Thank you very much, Pavel. Hello, everyone. I'm very happy to join you from San Diego today. It's an early morning here at 4:40 a.m. And I'm happy to present to you now the existing solutions that have been developed with the EOSC and with EBRAINS together. So we will see how different European projects create synergy and together work towards a common goal. The World Health Organization has the goal of a global health data space, and the European Commission wants to create a European health data space. And we have the European interoperability framework that defines technical interoperability elements that comprise, for instance, applications and infrastructures, linking systems and services, interface specifications, interconnection services, data integration services, and secure communication protocols. As you have heard before from Jan Bjarne, the Human Brain Project and its platform EBRAINS share these aims, with a focus on the brain, the part of our body that contains the most personal information on the data subject itself and their health. So therefore, a vision of EBRAINS was to create a trusted processing environment ecosystem where users can run complex analysis and simulations of personalized digital human twins. So not just for sharing sensitive data, but also creating digital workflows that enable full provenance tracking and lineage of data. It is a well-accepted fact, and Jan was mentioning this before, that the majority of research results are non-reproducible. This is known under the term reproducibility crisis. The lack of non-reproducibility of research we do also find in the fields of neuroscience and computational neuroscience. The consequence is inefficient science and lack of breakthroughs that benefit patients with brain diseases. And this problem is, for instance, highlighted in this Science article in 2016. Here it reads, for instance, data, code, and workflows should be available and cited, and only then science becomes reproducible and efficient. In 2012, I was involved in the first release of the virtual brain simulation platform that I was leading together with other colleagues. The platform allows to integrate many different brain measurements of a person, of an individual, in mathematical models, and it creates personalized in silico brains that we can simulate. So this is an international project initially funded by a US foundation and now by multiple international and national grants. When I had the opportunity to join the European flagship Human Brain Project in the year 2018, this was 5 years after the start of HBP in 2013, the Human Brain Project had established already several platforms to support neuroscience with digital infrastructure. The neuroinformatics platform, the medical informatics platform, high-performance computing platform, the simulation platform, and the neurorobotics and neuromorphic platform. There was leading now the new established co-design project, the Virtual Brain, that had the goal to connect the components and services of different platforms and make them all together support the services of the virtual brain simulation framework. So users wouldn't have to deploy the virtual brain software on their own computers. They just started on EBRAINS Cloud and use the high-performance computing Phoenix backend for heavy computations. Users can build models from the data available in EBRAINS, and they can use workflows that do exist already and publish their results again on EBRAINS. So one of the biggest challenges in creating such an interoperable infrastructure is given by the fact that human brain data are personal data and brain data are health data. They fall under GDPR, a new law that also had come in force in the same year in 2018, when the co-design project, the Virtual Brain, started. So we had to develop the envisioned interoperable service platform with the proper technical and organizational measures that protect the privacy of the data subjects. In brain health research, most often anonymization of data is not an option, as mentioned by Jan, because it is the brain data itself that contains the identifying information, and this unique information is exactly the basis for the research being done. So 4 years later, in 2022, after establishing the co-design project, we had actually achieved an infrastructure that enables interoperable digital workflows for personalized brain simulation events with all the technical and organizational measures in place to protect the data. And this was described in this publication, Brain Simulation as a Cloud Service, the Virtual Brain on EBRAINS. So several virtual brain services were interconnected with the EBRAINS core services. For example, with the knowledge graph, with the cloud services, with the high-performance computing backend to provide the compute power and the storage needed. But also with other services like the digital atlases to retrieve biological information and incorporate it into models, or the neurorobotics platform to visualize the outputs of the dynamic brain. So now I show you a couple of very concrete examples how this looks like. So this is the entry page of EBRAINS, and you find the different service categories. You can choose the simulation services. There you have the whole brain simulation services, and you find the virtual brain simulator software page, and there you find buttons to access different services. So you can start directly the software, and you get the graphical user interface that you otherwise would have on your own computer after deploying the software locally. Now, using the cloud service of EBRAINS, it is possible to set up a personalized brain simulation with all the protection measures in place that are needed to protect the privacy of the data and run complex simulations with the compute power provided by the Phoenix compute centers. Another example are the automated digital workflows. We provide them for the processes that are needed to generate the data that build virtual brain avatars. And these are mostly neuroimaging, brain imaging data. So we have very complex processing flows that are available in Docker containers that are reproducible, that can be deployed on any system, on any of the back-end supercomputing centers, and that also provide, on top of the processing, the needed data protection with encryption of the data, sandboxing of the data when they are decrypted, or also access control. Another example is interoperability with other simulators. The virtual brain provides a course degree simulation of the brain, but there are other simulators that provide more detailed modeling on the level of single neurons or even beyond. And it is now possible to set up computational models that have different degrees of granularity. Here you see, for example, the nodes modeling the brain at the core scale, and here are much more detailed spiking neural networks that can be embedded in such coarse brain models. And through the interoperability that has been established amongst the simulators, it is possible to simultaneously run simulations at the core scale and for some defined structures in the brain at a much more detailed scale. And this is an example where this has been used to model deep brain stimulation, having the basal ganglia and thalamus network simulated at a very fine scale of single neurons, producing spike trains and firing rates, and the rest of the brain is simulated at a coarser scale and enabling, for example, seeing the impact of deep brain stimulation on cortical motor regions of the patient. And this is to optimize on an individual level the best possible kind of stimulation for a patient. Yeah, another example is the interoperability with the digital atlases. Here you see, for example, how we can access via the standardized API of the atlases information available there. In this case, it's a receptor distribution of the human brain. And since we have common anatomical reference coordinate systems, we can directly pull this information in our brain models and make the brain models much more biologically realistic. Another example is the possibility to interface with knowledge bases, such as pathway inventories. And with this, we can query information how pathways are changing, for example, in brain diseases, and incorporate these altered pathways in our brain models to make the simulations even more realistic. So at the end, I show you one example that has been recently established. This is a connection between the virtual brains and the neurorobotics simulation platform. This allows to see what is actually the functional outcome of the altered dynamics in a simulated brain. So we can see how different personalized virtual brains differently perform, execute motor function, for example. And we have now all the mathematical means available to analyze and infer the source of these behavioral or functional differences in individual subjects. So in the same year, when the co-design project, the virtual brain, had started and the human brain project, the EOSC project, Virtual Brain Cloud has been kicked off under my lead as well. There, the vision of the 16 involved partners, some overlapping with the partners in the human brain project, was to create an entire infrastructure for sensitive data with data protection by design and by default. The Virtual Brain Cloud project became the partnering project of the Human Brain Project and EBRAINS very soon. And now, also 4 years later, the main output of the Virtual Brain Cloud EOSC project is a secure virtual research environment that has several functionalities. So here you see a high-level architecture. It has a front end with user-facing services. It has interfaces to hospital data sources like radiologic imaging data management systems or other structured data bases such as RedCap. And a secure core zone to process and manage the data with several functionalities and the services available to the users. Technical and organizational measures provide the proper data protection for the sensitive health data. Some technical measures are listed here. They comprise the critical infrastructure certification of the IT infrastructure used to provide the services, isolation of data and resources achieved on several levels, data encryption, authentication, authorization, and a very fine-grained and role-specific access control. The solution also supports the organizational processes around data sharing and data management, some of which were also mentioned before by Jan Bjarne. For instance, checking for the availability of a proper patient consent, the ethics code, the sharing or processing agreement, the service agreement that specific technical measures are in place to protect the data, and the most often needed data protection impact assessments that are required if health data are being processed on such digital infrastructures. So a recent EBRAINS project that started in 2022 is the Health Data Cloud. It uses now the technology, the secure virtual research environment developed in the EOSC project, the Virtual Brain Cloud, to build a federated interoperable system of nodes that provide services for sensitive data. So we have here the central node of EBRAINS, this IT infrastructure provided by the Swiss supercomputing centers and other Phoenix partnering high-performance computing centers. And we have satellite nodes that also provide their full-fledged services. For example, at the Charité, the Oslo University Hospital, or other, in most cases, university hospitals that already underwent critical infrastructure certification and that are enabled to provide the technical and also organizational security measures to provision the service for sensitive data. And even so, these satellite nodes are completely functional on its own. They will be interoperable with the central platform, and the central platform has the services that provide the discoverability of the data in the central platform and the satellite platforms to the global users, the users in the European Union and beyond. And this is achieved by sending the metadata from the satellite nodes to the central knowledge graph. And interoperability is also achieved by shipping the code that is being deployed on the central platform of EBRAINS to the satellite nodes as needed. For example, if data sets are stored at the Charité satellite node and the processing shall be performed locally using the local high-performance computing facilities, then the users can easily pull the Dockerized containers that contain certain workflows to the decentral infrastructure and apply it to the data there. So the shipping of the data is not necessary. And the user journey of this currently built infrastructure looks as follows. So there's a data discovery service, data can be searched, and this has been nicely explained by Jan before, via the knowledge graph and the available metadata that are also being developed in EBRAINS. Then when useful data have been discovered, there's a possibility to apply for a permit to access these data, and there are also digital workflows to review such applications. Authorized persons to do this, according to GDPR, are the data controllers. So there's not a centralized authority that provides the permission, but it's the actual data controllers for each specific data set that will be enabled to review the applications and to establish the required contractual agreements, sharing agreements with potential users before providing access. So if the access has been provided, then there are services for using the data, and these comprise, for example, the simulation services, but also Atlas services and the workflows that then can be used or advanced by the users to process their data. And finally, the research will lead to new results, new data derivatives, and they on its own are attractive for other users potentially. So there will be support in annotating those output data in a semi-automated way and to ingest the outputs, the results again, via the knowledge graph to EBRAINS and making them by this discoverable. And with this we close the loop of this user journey. And we have first examples how these new technologies lead to medical innovations with the capability, for example, to augment the prediction of disease trajectories and dementia, also with the capability for digital drug testing on eBrains and for in silico intervention planning, such as the deep brain stimulation work that I have shown you before, or other interventions such as neurosurgery, for example, in patients with epilepsy. And with this I come to an end of my presentation, and I thank you very much for your attention, and of course I thank all the colleagues who contributed to this work.
Thank you very much, Petra, especially given the early time of the day in San Diego, where you are at the SFN conference, so much appreciated. And you have shown us very clearly how the eBRAINS tools and services are already anchored in the development of EOSC over the years, with virtual brain cloud having been an EOSC project. You have talked extensively about interoperability and how the very principle, in particular given the size of brain data sets, is to ship the code rather than the data, to make the code visit the data. And last but not least, you have taken us through the evolution towards a complete infrastructure with some presentation of the applicability cases, which of course is very meaningful, because after all this effort is needed to serve a purpose. And the higher predictive value of computational models is already showing its effects, and that's of course good news. So this completes our round of presentations, and before we finish, we would like to ask if there are any questions to what has been said. Yes, please. Yeah, if you could maybe use the microphone so that Petra can also hear us in San Diego.
Roxana from Cyfronet Computing Center in Krakow. Thank you for wonderful presentations. And I was wondering, of everything that has been presented, which is something very big and something to look up to probably in the future, but trying to have a bigger context in EOSC as a place where we try to come up with central standards. So three matters got my attention. First matter is the approach towards the sensitive data, because I believe it has also been said that your initiative is one of the few that has taken it so far already. And I was wondering whether one of the outcomes could be some generalized approach that might serve the others who want to start dealing with the sensitive data but has no idea where to start even. Because many institutes have not plans, but ideas for new projects, and that might include sensitive data, but don't even know where to start from. And something like that can be a big advantage for this kind of initiatives. And the last matter is about the interoperability. You mentioned two types that I caught. The first type is about being able to integrate different types of data for the sake of including different types of data to simulate and use the model of a brain. And the second one was exactly about transferring the analysis tools instead of transferring the data, which is easier. Would you say it's scalable? Would you say, because we now are in the moment probably in EOSC where everyone is introducing some solutions to fit the use cases. So in your case, it was moving the Dockerized tools for the sake of running the simulations, but something similar is happening in Polish infrastructure peer grid, where to achieve the interoperability, we have the applications supporting different use cases installed on every computing center involved. It's not as, let's say, scalable as yours, because you can move the Docker instance in Docker packages. But would you say it might be something that you would propose as a general approach towards the interoperability between, at least for some of the use cases, and the same for the data? Because some communities are trying to make some kind of crosswalks between the different metadatas, and for you, you didn't give the details, or I didn't catch it, for the, putting all together different types of data in order to achieve one model of brain in your case. Thank you. I'm sorry for being long.
Okay, thank you very much. So super interesting questions. So the first one on sensitive data and whether our experience can be helpful to others. Of course, we are not at the end of the journey with respect to ways of dealing with sensitive data. However, some concrete achievements have already been done, as we have heard. And the second question on the scalability of our interoperability solutions, right? Shall we go to the sensitive data question, Petra?
Yes, thank you very much for the great questions, and thanks Pavel for handing over to me. I'm very happy to address the sensitive data solutions questions. So the developments that we are doing as part of the EOSC Virtual Brain Cloud and also the EBRAINS Health Data Cloud are all open source. So the intention is really to create an ecosystem that utilizes these developments, maybe further advances them, but certainly not to restrict access to them. And this includes very comprehensive documentation for developers that is being produced, but also for administrators and operators who run the software and are responsible for maintaining the software and their entities. Also, what helps to further distribute the solutions is that we got now additional synergistic projects funded via the European Commission. One via the Horizon program, this is called EBRAINS Health, and several new partners with data sources are being on board there, and the goal is to transfer the solutions to their data centers, so not getting their data, but really ensuring that each center has their own service for sensitive data and is able to provide the interoperable interfaces to connect with the central EBRAINS platform. Another project funded under the Digital Euro program is the Testing and Experimentation Facility Health AI and Robotics that has the goal to bring the services not just to academic users, but to startups and SME and SMIs, and eventually also the industry sector in general. And also this is a very large-scale project funded by 60 million euros that starts in January next year. with the goal to make the developments much wider available than they are at that point.
Okay, thank you very much, Petra. I'm also tempted to ask Jan about the journey of EBRAINS with respect to sensitive data, because we have come to it at a fairly late stage, but deliberately so as well, because we primarily work with research data and anonymous data. Now, strongly pseudonymized data is also accessible through EBRAINS, and we are becoming equipped with the sensitive data solution. But maybe you could comment, Jan, about sort of the journey of EBRAINS itself with respect to the different types of data.
Yes, I'm happy to do so. And I think when it comes to the knowledge graph and the services I explain, the knowledge graph itself and our services can take all metadata as long as the metadata are anonymized. There is quite a lot of information that you can share also from collections of data from human subjects, where you cannot share the full, deeper type of information, but more superficially, which can make the data discoverable, so that you will find out that they do exist, some of the main characteristics of the data, and you find out where they are, and also be given information about how you possibly can proceed if you would be interested in getting access. And in the worst case scenarios, it would be many steps to get there, but at least that it's identifiable and possible. So the services are general at the level of being able to take any kind of metadata as long as the metadata are anonymized, and then there will be layers behind. So that's our approach at this stage.
Great, thank you so much. Would there be any other questions or comments right now?
So maybe
Yes,
if I may comment on the second question regarding the scaling of workflows, automated digital workflows, and bringing code to the data. Indeed, workflows often are very specific for a certain use case, and with this, often they are not broadly usable by a broad community. But what we are developing in EBRAINS particularly are workflow management systems. So it's possible to modify easily the workflows and to adapt the workflows in a pretty simple and straightforward manner to adapt them to the needs of the individual use case. And with this we get a much higher flexibility, and on the other hand, for the users it's not needed, for example, to be proficient in programming themselves, but that they can use these workflow tools to adapt the workflows according to their own needs. And with this we hope that also the workflow solutions become scalable and useful for the broader community.
Okay, thank you so much. So I hope that goes a long way to answering also the second question. And I'm just having a final look if there are more questions. Yes, please. If you could come to the microphone, yeah.
So federated AI was mentioned. Is EOSC life science login being used by EBRAINS in any sense? I know you have a EBRAINS login, but is the sensitive data aspect making it difficult to use something like life science login, which might be too general purpose and not safe enough for sensitive data? And then also going further to the state where EOSC is developing EOSC AI, which is a federation of these science cluster AIs such as EOSC Life Science Login.
Great. So maybe both Jan and Petra could share their opinions, starting with Jan.
Yeah, I think it's a very important question, and there is a need to have more crosstalk around these type of login routes, definitely. So the one we have for so-called EBRAINS accounts, which is what exists at this point in time, that is set up in such a way that we verify the individual people requesting the accounts. They have to have an institutional email. We check the existence of the institutions and the relevance, or they have to identify through passports. So basically, we don't have any Donald Duck at Gmail type of sign up at the moment. So that's how it works. So we are able to track individuals when it comes to the very few, I must say, privileged things they can do, which would touch upon the sensitive area. Most of these things is related to the fact that we need to have some control of the use of the resources that they get into if they have these accounts. We have about 6,000 now from around the world. Only restricted by embargoed countries according to EU rules, but other than that, completely open. Petra, excuse me?
Yeah, thank you very much, Jan. I think you covered it very well. Maybe just one addition. So we are using Federation of AIM already, and so we are not federating with EOSC AIM currently, but this is something to be explored, and in principle, technically, would be feasible in the future.
Sorry, I wanted only to have a little bit of detail. Is it enough to be an affiliated researcher, or do you need to be affiliated with a certain research institution?
It's enough, well, to have it, let's say, automated. You need to have an email account from an institution which we can identify as a serious actor. So if you have an other email, there are a couple of more steps, but it's fully possible to get the account. Yeah.
Maybe to add to this, the health data cloud services go beyond this. They are federated with EBRAINS, of course, but for ensuring the identity of an individual user, which is very relevant in the context of handling sensitive data, it is required to provide, for example, the identity card, so in terms of the ID number, but also the document with the face, and there's a face identification of the user.
Last time, sorry. I asked this question because I was wondering about the feasibility of a general AAI infrastructure for EOSC, and I wanted to understand that in your use case, if there was another identity provider who is also checking the research affiliation of a researcher, would it be enough for you? Because what AAI is now developing is the AAI proxy, so the possibility to connect different identity providers. There is Gmail as well, but there is something also called the trust of the user. And I was wondering if one of the attributes was telling if a given identity provider is checking, in fact, the affiliation of the researcher, would it more generalize the possibility to give access for the researchers from other identity providers than yours? So that's why I asked if you have only listed affiliations or researchers in general.
Yeah, well, I can only say I really appreciate the question. It's super relevant. And if you ask, are we doing this systematically? No, the answer is no. Do we want to do it? Yes. So this is the direction we need to go. So it's a bit more manual at this point in time. It's related to the fact that this is, what should I say, relatively new. I'd also like to emphasize that there is quite a lot you can do without these accounts. So all the search is open, for example, and there are also many tools that are openly available, but you do need the accounts for a number of purposes. What you point to is extremely valuable and clearly a direction that we have to go in.
Okay, thank you very much. I'm just looking around for last questions or comments. Yes, please.
Hi there, this is Reagan. So really nice presentation, thank you. So I'm a bit of noise graph guy as well. So could you tell me if the noise graph could represent, how do you represent the temporal information into the noise graph? Because all the time I was doing my PhD, so we had a bit of situation representing the temporal information. With spatial, we used to have good annotations, but representing the temporal information was like really difficult part of that. So that's one question. The other question is, so if I use eBrains, so would it be possible to ask some questions like, okay, show me everything that's there about Alzheimer's disease, and then you'd have all the information about Alzheimer's disease, and at the same time, if I am to ask, okay, show me all top entities that come in between Alzheimer's and Parkinson's disease. So would it actually answer those sort of questions?
Yeah, we're getting somewhere here now. So I think we need to go into this one, both Petra and myself. I can just begin by saying, when it comes to your question about different data types, such as time series data, temporal data, and so on, I would prefer to rephrase your question. I certainly understand it, but to rephrase it and say, how would our metadata framework deal with those type of data? Because as long as that can deal with it, that is built into the knowledge graph. And do we deal with those type of data? Yes, we do. So we have what we call extensions to the metadata model. These extensions go into different areas, such as the area you point to. And next question, can you look at what's happening? Yes, you can, because the OpenMinds metadata model is available at GitHub. Will you find today what you want? I'm not entirely sure, but I know we are working on those kind of extensions. So that's definitely coming, if it's not already partly available. When it comes to your question on the different type of diseases, different type of how we can bring together, well, if I interpret your question a little bit in the direction that there are, for example, presumably quite a lot of similarities in many of the brain diseases, and there's also research going on there in terms of mechanisms and common mechanisms and so on. I'm curious to hear if Petra has some thoughts on this exciting question. To me, it finally comes out of the box when we are able to differentiate the different pieces of information we have and organize them properly, and at the same time have top-down perspectives, let's say theoretical and paradigms, going into these data. That's my immediate thought, maybe not as concrete as you wanted. Do you want to add to this, Petra?
Yeah, I think you elaborated already very well. I think it is actually the major point and benefit of eBrains to work down to the actual mechanisms. By integrating all available data of a patient, but also additional data from the atlases that cannot be acquired in individual patients, and from knowledge bases, into theoretical frameworks that then allow, via inference, to infer the actual underlying neuronal interaction patterns, for example, or processes that are changed during a disease. And this is what leads to the change of function in patients. It's the change of neuronal activities that usually we cannot directly access in a patient. And indeed, it is expected that between different disease categories in various domains, also different psychiatric diseases, for example, psychosis or depression, that they actually have common pathways that are altered, and a lot of commonality in terms of the underlying mechanisms. Usually it's a spectrum of mechanisms, so there's not a single mechanism per disease category. And the possibility to work down to these origins, to the actual mechanisms, enables us potentially in the future to come up with a completely revised classification of brain diseases that is based on the actual mechanisms that then also will guide the possible interventions to be provided to the patient.
Excellent, thank you so much. So with a couple of minutes remaining, this will have to be the last question or comment. Yes.
Yann Lefranc from eScience Data Factory. I have a question. So one of the three pillars of eBrain is curation. Who is doing the curation and how is it maintained? Do you have already an infrastructure? And linked to curation is the link of documentation and metadata. How is it linked with ontologies? So how do you use the wealth of biomedical ontologies that are out there in eBrain?
So maybe ontologies first. Yes, I didn't go much into the details of what is this metadata framework. It contains controlled terminologies, and it uses the ontologies that are available, and also some of the teams are contributing to ontology work. Just as an example of that, we have one on the way called Atom, which is actually dealing with Atlas ontologies, because that was missing, whereas we are using a number of other ontologies and also available data models. So the whole purpose of having a metadata framework is to really make use of all these available ontologies. Then who are they? Who's doing this? We're working with a team of people who basically operate along three axes. One is on the more fundamental aspects, such as what you asked about, on ontologies. The other is on the tools aspect, on giving the data providers the tools they need so that they can automate as much as possible or work in a smart way. For example, collect metadata early on in a form that can be easily shared, develop the tools. And number three, be available for questions, Q&A, and interact when data are submitted to our system, when they have to provide metadata. So they can also have a Q&A and a direct interaction. So that's what they're basically doing. There are teams available in 3 locations in Europe.
Great, thank you very much. Now with these questions, very interesting and valuable to us as well, we have reached the end of our hour and a half together. So we would like to thank you for your interest in eBrains. We will be around for a large part of the EOSC symposium, so if you would like to talk more, then you are more than welcome, of course. And feel free to contact us at eBrains in our different capacities. But many thanks to Petra for joining from San Diego, Jan as well. Many thanks, and thank to all of you for coming and for your interest. Thanks so much.
Thank you.
Thank you.